server. Okay, so let us do something that is a little bit different today, as promised. One second. How many of you have had some quantum stat mech at some level or another?
Maybe a splash. Very
What?
small splash.
I'd say the same, maybe like a splash in
I couldn't hear
undergrad.
you properly.
I've heard you mention the word.
You guys are all muted. I think Bailey is the only one who's not muted. Bailey, what did you say?
I said that, you know, I've had a splash of it, just a very small exposure to it.
Okay. Anybody else has had any quantum stat mech?
I said about the same, like we got a very brief exposure to it in undergrad.
Okay. All right. So I'm assuming that basically means that this stuff's pretty new to you, because that'll set my speed and how much I'll cover in a way, because it's a funny subject. It's like once you get into it, it can be pretty hard to get out of it, because nothing about it is easy. Everything is hard in this subject. Yet it can be done for practical purposes in a very sort of light way. So I'm going to try and steer a middle ground. So because that's the only thing I can do. I mean, if I want to get seriously into it, it'll be full course. If I want to get too light into it, none of us will enjoy it. So fundamental problem in studying quantum many particle systems is the fact that calculations are nearly impossibly difficult. That's a fundamental problem. Why is that? Well, because the algebra of quantum mechanical particles is pretty weird. And we kind of, I hate to say this, but we kind of do the algebra with the help of a certain set of rules that we pretty much are sure that they hold up. But why they hold up, we seldom really understand. And when I say we seldom really understand, I'm being very generous, because quite honestly, I don't think we really understand it. Very few things we get. And what I mean by very few things we get is very few things we get with any kind of intuitive relatability. Okay, so the intuitive relatability, ability to predict what might be the outcome given what we know, is relatively poor in the quantum world, especially in the quantum world of many particle interacting systems. So naturally, the next best compromise, almost always a starting point, is the quantum world of non-interacting many particle systems. Now, you'll obviously be wondering, what is the difference between a non-interacting many particle system and basically a single particle system? Because is it any different than studying a single particle system? That's a question that you can legitimately ask. And you can say, well, an interacting many particle system must be fundamentally different than a non-interacting system. So this particular point alone deserves a little bit of discussion. And I'm going to start off our discussion in that spirit. You see, quantum particles have weird tendencies. So let's go into the intuitive aspect of it. And I've talked about this in class. Quantum particles have weird tendencies in the sense that if you have bosonic particles, which means integer spin particles, then these integer spin particles behave a certain way. And we also know that the non-integer spin particles, which are the fermionic particles, they behave in characteristically different ways. But that is irrespective of the interaction itself. So if you have 2, 3, 4, 5, 8, 10, 15, few million bosonic particles or a few million fermionic particles, these particles will behave fundamentally differently because of their quantum mechanical properties themselves. This particular kind of quantum mechanical properties is often what we call quantum statistics, because this is not seen in classical particles. This is very special to quantum particles. So non-interacting quantum many-body systems essentially can still be effectively interacting because of the quantum statistics, because of the way, meaning because of the way the fermionic particles behave and because of the way the bosonic particles behave. That's what I mean. So we are going to look into this aspect of the problem right now. And this aspect of the problem is actually extremely intriguing, and we probably don't discuss it enough when we teach this class, because we don't know how to discuss it very well. That's the problem. Okay, so I'll come to that in a minute. So first of all, if you take identical classical particles, so they're all the same, no distinction between them. You make perfect particles. They're absolutely identical, and you put them in different places. You give them certain evolutionary conditions, let's say, obey Newton's laws, obey some other laws that you give them that make sense. And you can perfectly well describe their trajectory out to infinity in time and space, if you wish, right? So identical classical particles, they're distinguishable. You know where each and every particle is going to be as a function of time, and you can hence describe their time evolution really well. This is very intuitive for us under good circumstances. If we have the intuition, if we know how they're supposed to work, this works out quite well. We know, for example, how the Milky Way galaxy would look like a few billion years hence, and we are probably quite right about it as far as we can tell. We can predict, for example, what might happen when two different kinds of galaxies collide, or the fact that the whole solar system and everything is moving towards the Virgo cluster. These are well-known facts. Imagine how difficult it must be to predict something like that. But we do a good job. I mean, for thousands of years, tens of thousands of years, people have predicted solar and lunar eclipses. There's a huge history of this. There's a story of the church about it. There's a story of the Vedas about it in India. People from Iraq and Iran and all those areas, and have done calculations. Latin American ancient civilizations, Incas and the Mayas, they have done their calculations. Many of them are really old. These are things we know. So that kind of classical dynamics has been very well established. We know it well. The quantum world, on the other hand, poses some really weird problems. So The biggest issue is that the quantum particles are indistinguishable. Okay, so we can't really say particle 1 and particle 2 if they're identical. Okay, because that 1 and 2 has no meaning. Because we can say this is particle 1, this is particle 2, but a nanosecond or a picosecond or a femtosecond later, you don't know what happened to your particle 1 and what happened to your particle 2. You don't know which is which. Everything is everything's twin. Okay, so, and you can't distinguish. So therefore, quantum mechanical particles have a fundamental difference that they are indistinguishable. And because they're indistinguishable, how a collection of quantum particles will behave, therefore brings up unique issues. So suppose you have a few particles, let's say A, B, and C, and they are in states XA, XB, and XC. Okay, they're in these states. Now suppose that you ask the question, you don't get into time evolution and so on right now, then you have to get into either using a wave equation like a Schrödinger equation, then you have to, of course, identify the particles with the waves and go that route. Time-dependent Schrödinger equation. Or you have to use a Heisenberg equation of motion, in which case you have to define the operator algebra and use the commutator brackets and so on to describe evolution, and then you have to go back to measurability, observability, by going from the operators to probabilities. Either way, let's not get into that evolutionary dynamical issue, but you can certainly ask the question that what happens to the particles at some later time t. So let's look into my notes here and say, what would be the wave function describing the states of the three particles psi of xa, xb, and xc at time t? Let's say we ask the question. And as I said, one can no longer say that at some time t, of course, a later time t than when the system was initiated, A will be at xa, etc. We have no way of saying that. So if there are three particles, then there are 3 factorial, which is 6 ways to arrange the particles. And we don't know which of these ways is how the particles have ended up at any given time t. So, so this is a real issue, right? So at time t, along with the wave function, the possibility of what might happen with pairwise exchange of particles must be considered. So the very fact that you're asking the question of what state the system is at a later time t, because you don't know which particle is which, you have to take into account what might happen if the particles have interchanged positions and so on, because that's a very real possibility. And if particles interchange positions, then the quantum statistical properties of these particles will kick in, and that's what we'll be looking at. Okay, so here. So since the particles are identical, the physical observables associated with the wave function, where A is at xa, B is at xb, etc., are the same as A is at xb, etc., B is at xa, whatever. So if you want to look at the probability, so psi star psi of this whole thing, let's call it rho, then psi star psi or psi mod square somehow should be unaffected by any exchange, right? Because particles were there, the particles are here. It's rho, which is the probability square is the same, and this psi star psi is the same, and so whatever exchanges have happened must not affect this probability. The probability must be conserved. So if that is the case, then let's say psi 1 is the wave function involving xa, xb, and xc, and psi 2 is the wave function involving xb, xc, and xa, right? So there's been some interchange. And basically what we are saying is that rho equal to psi1 mod squared is also equal to psi2 mod squared, because the probability is the same of finding the three particles. So that means what is the relationship between psi1 and psi2 can now be examined. Clearly, psi1 and psi2 should not be exactly the same. There should be a difference. But then psi1 star psi1 is equal to psi2 star psi2. So naturally, that means that psi1 and psi2 are related by some kind of a phase factor. And so psi1 can be thought of as e to the I theta times psi2. So that's a natural sort of conclusion that one must reach. Now think about it intuitively. Let's say psi1 is a physical quantity. It's not, we know that. Psi1 mod squared is a physical quantity. But let's just say somehow we still can get a hang of psi1. And let's just say we still can get a hang of psi2. What really is happening that distinguishes between psi1 and psi2 such that we have to stick in this e to the I theta, which is cos theta plus I sine theta, in there. Theta is obviously some angle. That angle will give some contribution. So e to the I theta will have a real part, imaginary part, what have you. This is very non-intuitive. I mean, it's hard for us to wrap our heads around it. So it turns out that it was pretty much inferred based upon whatever thinking experiments were possible in the early days of quantum mechanics, that this theta should be 0 for integer spin particles or bosons, and this theta should be pi for non-integer spin particles, which are the fermions. So therefore, theta equal to 0 essentially means that psi1 is equal to psi2, but if theta is equal to pi, then that means the minus sign would kick in psi1 and psi2. Now there is an interesting twist to this. This particular behavior, it was also observed in time, only holds up in 3D space. So if you are in 2D space, then this behavior is not quite the same. In fact, in 2D space, bosons and fermions have fundamentally different behavior. And that is captured through the concept of anyons, which is a generalized boson-fermion kind of thing. So many of these things have been around for a long time, but they have been taking shape as hard concepts in physics. I think of the last 30, 40, 50 years or so. So anyway, one would think that, something as elementary as a bunch of non-interacting quantum particles should be relatively simple to follow. But as you can tell, that's not the case, right? So this business that I just said, this theta equal to 0 being behavior of bosons, theta equal to pi being the behavior of fermions in 3D, this stuff is captured in what's called the spin statistics theorem. Okay. And I'm going to tell you a little bit about the spin statistics theorem in the sense of what a mess it is, but I'm no expert on it. So I beg my ignorance and that you read the paper, because I'm also looking at the paper myself. I've not really dug into it in a big way thus far, but I'm very interested in it at an intellectual level. So if one interchanges two identical particles, their wave function changes by either +1 or -1. That's one of the core messages of the spin statistics theorem. The second core message is, if you turn a particle around, suppose you could grab this particle and turn it around by 360 degrees, not 180, not 45, a full 360 degrees, the wave function changes phase by either +1, which means it doesn't change phase, or -1. For bosons, it's +1. For fermions, it's -1. This is always the case. And this is what the spin statistics theorem essentially tells us. So 1 and 2 here are not independent choices. That is, bosons behave the same way in both 1 and 2. Okay, and so do the fermions. So in both, the interchange would mean that for bosons, there will be no sign change of the wave function. For fermions, the sign change of the wave function would be -1. And if you grab a boson, turn it around, there is no phase change of the wave function. Grab a fermion, turn it around, phase change of -1 will kick in. And it doesn't matter if your boson is a photon or a Higgs boson. It doesn't matter if your fermion is an electron or some heavy fermion in some fancy material. It is what it is. That's what their property has been seen to be. So before I move on from this rather confusing, intriguing, annoying, whatever you call it, observation, I wanted to give you a bit of a window on how vexing this problem has been. So I suppose you know, or most of you at least may have some idea, that quantum mechanics has been a very problematic, controversial, intuitively opaque, and yet full of surprises kind of an area of physics, right? Because things are weird out there in a quantum world. One of the very, very interesting names in physics itself, in theoretical physics itself, and certainly in the study of Rand unification theories and so on and so forth, is this gentleman here. This is George Sudarshan. George Sudarshan was an Indian-born physicist. He, in fact, just passed away a few years ago. He used to be a professor at University of Texas, Austin. But George Sudarshan was a legendary figure in physics. He also had a very accurate personality. George Sudarshan was not somebody that you messed around with. And if you didn't like what you were up to, you didn't want to be on the other end of George Sudarshan. So he was not a very well-liked man by many, certainly by many very powerful figures. And that cost him very dearly. That cost him 2 Nobel Prizes, no less. So the first Nobel Prize that George Sudarshan did not get, for which you don't hear his name, is the Nobel Prize that went to Gell-Mann and Feynman, which is for quantum electrodynamics. So much of the fundamentals of this field was set up before, if not simultaneously, by Sudarshan, and Sudarshan had actually shared his work with Feynman and Gell-Mann. So they did interact. They were very much aware of each other's work. They were very much big players in the development of quantum electrodynamics. But Gell-Mann and Feynman got the prize, and Sudarshan was not there. That was the first Nobel Prize he didn't get. And the second Nobel Prize he didn't get was the Nobel Prize for quantum optics. So the fundamental theorem of quantum optics, for which Roy Glauber got the Nobel Prize, and this was about 10, 12 years ago, or maybe 15 years ago. Glauber used to be a professor at Harvard. That work was done simultaneously by Glauber and by Sudarshan, with Sudarshan's paper coming out before Glauber's. But again, Sudarshan didn't get the prize. So anyway, I can go on. But Sudarshan was a remarkable man. And this particular paper, which is very accessible, by the way, I can put it up on our website, on our UVLearn's website. I haven't done it yet.
Please do.
Okay, I will. It says toward an understanding of the spin statistics theorem. Now, it is not easy to understand this paper either, but this is one of the better papers that are around regarding spin statistics theorem. Okay, so let me just spend a little bit of time going through the abstract, because it tells you what a mess it is, the spin statistics theorem. It says we respond to a recent request from Neuenschwander for an elementary proof of the spin statistics theorem. So that's the purpose of the paper, is responding to this comment by this gentleman Neuenschwander about how do you figure it out and what's your proof of this. First, we present a pedagogical discussion of the results for the spin zero, so boson, Klein-Gordon field, quantized according to the Bose-Einstein statistics. All right. So this is a four-dimensional wave equation kind of a thing. That's what a Klein-Gordon field is. And for the spin 1/2 Dirac field, quantized according to Fermi-Dirac statistics and the Pauli exclusion principle. So that's what he's trying to do, a pedagogical discussion to kind of lay out the field. This discussion is intended to make our paper accessible to students familiar with the matrix solution of the quantum harmonic oscillator, which almost anybody walking on the face of the earth nowadays knows a bit about. So in principle, this should be a very readable paper. Then he says, next we discuss a number of candidate intuitive proofs and conclude that none of them pass muster. So all the intuitive proofs that are around are wrong. The reason for their shortcomings are fully discussed. Then we discuss an argument originally suggested by Sudarshan, which proves the theorem with a minimal set of requirements. So this is now a rigorous proof he's talking about, which has a minimal set of requirements, which means it should be both necessary and sufficient that he's presenting. Although we use Lorentz invariance in a specific and limited part of the argument, we do not need the full complexity of relativistic quantum field theory, which is where the original proofs that have been around, which are impenetrable, came from. Motivated by our particular use of Lorentz invariance, if we are permitted to elevate the conclusion of flavor symmetry, which we explain in the text, to the status of a postulate, one could recast our proof without any explicit relativistic assumptions, and thus make it applicable even in the non-relativistic context. So he has actually extended the proof to a non-relativistic context as well. Such an argument presented in the text sheds some light on why it is that the ordinary Schrödinger field, considered strictly in the non-relativistic context, seems to be quantizable with either statistics. Finally, an argument starting with ordinary number valued commuting, and with Grassmann valued argument starting with ordinary number, anti-commuting oscillators, shows in a natural way that these must relativistically embed into whatever. So it goes on to something which is certainly beyond me at this stage, certainly at this hour. Now, this is an American Journal of Physics, which is generally to explain it to students. So as you can see, spin statistics theorem should not be mentioned lightly. And again, he's just responding to this poor Neuenschwander's proof request for
the fact that he mentions flavor symmetry seems very strange to me, because what flavors do we have if we're just looking at the basic non-relativistic Schrödinger field?
Well, he's looking at the relativistic part also, right? He's starting out with the relativistic part. And then
and then uses flavor symmetry to get to the non-relativistic. Is that what it says?
Let's go over it.
Down motivated by our particular use.
motivated by a particular use of Lorentz invariance, if we are permitted to elevate the conclusion of flavor symmetry to the status of a postulate, one could recast our proof. So in other words, if the flavor symmetry characters are generalized, one could recast our proof without any explicit relativistic assumptions. So basically, explicit relativistic assumptions are subsumed in that. That's what he's saying, I think.
Interesting.
Yeah. But you also have to understand that this guy was one of the founding fathers of, flavor concepts and so on as well.
Okay.
So he understood it better than most. But the paper is not easy to read. I mean, I've been working on it. I haven't had, honestly, the time and kind of ability to focus on it as I would like. But I hope to be able to kind of pick up on it as much as possible, especially if I can find any of Sudarshan's lectures online. There are a few, but not too many. He was a good speaker. I mean, I had invited him once, not to Buffalo, but I used to be the president of the American chapter of Indian Physics Association for many years, back in the early 2000s. And we used to give a lifetime achievement award to physicists of Indian origin in the US and Canada. And Sudarshan was awarded, and I was the president at the time. So it was my honor to award him the lifetime achievement certificate and medal. And he was a fantastic lecturer. I mean, there was no question about it. In spite of his personality, he was just a great fellow. So anyway, the Neuenschwander question actually appeared in 1994 in American Journal of Physics. And it's interesting that Feynman, in fact, in Feynman Lectures Volume 3, Chapter 4 talks about how impenetrable the spin-statistics theorem is, and that a satisfactory elementary proof is really needed. I mean, you're talking about the people who created quantum electrodynamics, right? Feynman, Gell-Mann, and of course, in his own way, George Sudarshan as well. Anyway, let's move back to the course, to the course material, because I don't want to spend too much time on this. But I just wanted to make you aware that spin statistics theorem is stated so casually, and yet it's one of the most uncasual things that you encounter as you learn quantum mechanics and quantum many-body physics. So anti-symmetry of fermion wave function, therefore, has important consequences. The most important consequence is, of course, the Pauli exclusion principle that we, that we are so very tied to and familiar with. And you can see it in the following way. Suppose XA equal to XB equal to X. So there is two particles are in the same state. Then psi, the wave function of our three-particle system, or minimal many-particle system, psi x comma x comma xc. So let's say x xc, and then say equal to minus psi xp x xc, but then they're in the same state, so xx and xc. The question can be, how do you understand this equation? And the answer is this equation can only be understood if psi is 0, right? So if psi is 0, that basically means you can't have xa equal to xb equal to x condition, which means that two particles can't be in the same state. So this is only possible, therefore, if two fermions can't be in the same state. So therefore, Pauli exclusion principle is kind of implied for fermionic systems, because this minus sign, of course, will only come in if we are using fermionic particles. So there are very interesting and important consequences, this being one obvious consequence that we are very used to. So let's just try to compute now something which is more concrete and, practical, like the partition function. So let's take a system of non-interacting particles in some orbitals, so they don't kind of hang out with each other. They have their own separate spaces in an atom. And we can try to compute the energy of the n particle state. So therefore, the energy of the n particle state here, E, is going to be the sum of the number of particles in a given state. So that's like an occupation number. The energy of the orbitals, which is the energy of the state, and the summed over all possible states that we are going to consider. Of course, you can see that this is just how many particles are in what state. And it's an accounting of that. There is no real interaction. And so this is a very simple summation of all the energies of the particles in the various states to get the total energy. So therefore, if you consider a sufficiently dilute system, meaning that these particles are not densely packed together, hence dilute in that sense, then the partition function for the many particle system would simply be, the partition function of the one particle system raised to the power n along with the Boltzmann factor. So therefore, you can say Z of n is Z1, which is a single particle. The Z1 to the power n over n factorial. So therefore, if we buy that, then the grand partition function Z TV mu is sum over n going from 0 to infinity, e to the beta mu n. So that's your chemical potential, and then Z of n, but the partition function of the system in the canonical ensemble, that's what this is. But we already know Z of n in the dilute gas limit is the Z1 to the power n over n factorial speaks here. So therefore, you write this as e to the beta mu, and then Z1, like here. The whole thing raised to the power n over n factorial. And then this, of course, immediately returns you an exponential function. So therefore, this becomes e to the beta mu Z1, but this piece, the summation then automatically becomes same as an exponential of an exponential beta mu Z1. So exponential of exponential you don't encounter all the time, but when you deal with fermions and bosons, many particle systems, it is very common to see them. Now, so you have e to the beta mu Z1, where Z1 therefore is sum over S, e to the minus beta epsilon S. And this is the single particle partition function. So therefore, sorry, what did I do? Yeah. So therefore, Z TV mu is e to the beta mu, which means this piece here, and then Z1 we put in Z1 here, sum over S e to the minus beta ES, and therefore we can essentially replace the sum, which is sitting on the exponential, as a product of exponential. So this is something we have been doing for a while, right? Because when we did the Ising model and so on, we did the same trick. So this is the product over all the states, e to the beta mu minus epsilon S. So what have we really achieved so far? You can ask this question. What have we achieved? We have taken non-interacting quantum particles. We have put them under the conditions of a dilute gas, so the particles don't interact. We say that there may be n sub s particles at energy state Es or epsilon s, and from that we have constructed a grand canonical partition function like so. And now, if you consider the equation of state, which you can get from the logarithm of the grand canonical partition function that we have talked about a great deal in this course, then PV equals KT equals log of Z TV mu. That's what we know. And log of Z TV mu, it's a very nice thing to do because you're taking log of an exponential of an exponential. You see, this is an exponential of an exponential. So if you take a log, then immediately one of those exponentials get eaten away. You are left with this piece only of the exponential. So therefore, you have KT sum over S e to the beta mu minus epsilon S. So therefore, the exponential of the exponential has now become a sum over the exponential. So this is relatively straightforward. It may look a little weird, but there's nothing weird about it. Normally, when we do a PV equals KT log Z, we also look into the occupation number business and the total number of particles that you must be able to get by summing up the average number of particles in each state. And this can be obtained by a del del mu, because remember, del del mu leads you to the N. So that's what we are after, NS. So del del mu of KT log Z, of course, you differentiate with mu. That means you get a beta popping out. So beta came out. Beta and KT cancel out. And then sum over S e to the beta mu minus epsilon S. And so that becomes sum over S of NS. Okay. So this then allows you to immediately identify something that we very well know, which is that NS is nothing but e to the beta mu minus epsilon S. This quantity here. So the occupation number in state S is e to the beta mu minus epsilon S. Now this is an interesting statement, actually. An interesting statement because in deriving this particular result, yes, we have assumed that the particles are indistinguishable, but we haven't imposed their Fermi or Bose natures. So we haven't imposed anything tied to their intrinsic spins. So as a result, this behavior is not for a fermion and not for a boson either. It's just generic under certain circumstances to quantum particles. So this actually is the corresponding Maxwell-Boltzmann distribution of energy for a quantum system where the fermionic or the bosonic features have not been explicitly imposed. Now, you can even think that the fermionic and the bosonic features would be explicitly entering the system's properties at low enough temperatures. So presumably at the higher temperatures, when the quantum aspects of the particles get more suppressed and the classical aspect of the particles are more enhanced, then what might be the distributions for the fermionic or the bosonic particles may actually converge to this particular one that we see in front of us, which is what we are calling the Maxwell-Boltzmann distribution. Now, I want to point out that this Maxwell-Boltzmann distribution, this particular energy distribution of quantum particles where velocities and all those things are not taken into account, does not look very similar to the Maxwell-Boltzmann distribution of velocities that you may have seen at some point in studying thermodynamics and so on. I did not spend much time on it, actually, in the development of the subject. But Maxwell-Boltzmann distribution of velocities, just for your own understanding, is that if you take a bunch of particles which have a distribution of kinetic energies in a system, and if it's a sufficiently large number of particles, then there is something called the central limit theorem. And the central limit theorem is a purely mathematical theorem, which basically says that if you have a whole bunch of things in a system, then there will be a typically peaked behavior. So in other words, there'll be some characteristic energy or something that'll show up, and where you'll find more particles, and then less particles have there'll be a bunch of particles with less energy and a bunch of particles with more energy, and those will kind of tail off. So there'll be a peaked structure. That's what central limit theorem says. And the central limit theorem is basically what gives you what is often called the Maxwell-Boltzmann distribution of velocities. This, on the other hand, there are no velocities. We are not talking about any motion. We're talking about particles and energy states only. It's a Maxwell-Boltzmann distribution of energies in these quantum systems. But it's still a Maxwell-Boltzmann distribution. It is still peaked about somehow connected to mu is equal to epsilon s, when this will be 0. Otherwise, if mu is less than epsilon s, this will be negative. And if mu is more than epsilon s, this will be positive. So the other thing is that it's a non-interacting system, so it shouldn't be surprising for you to note that beta PV is equal to n, because beta PV is this quantity here, and n is also this quantity here. So beta PV is equal to n. Same as that for an ideal gas. And we expect that. We expect the ideal gas result to be classical of quantum. All right. So now, yes, Denzel, go ahead.
Sorry, so on the last slide, you were saying that this distribution that we have is regarding energies, but doesn't really say anything about the velocities or kinetic energies. But I guess what I'm confused about is that since this is a non-interacting system, isn't the only source of energy that velocity, or isn't the only source of energy that kinetic energy? So isn't there a one-to-one correspondence between this and the...
The way I'm thinking about it is that we think that's why I talked about orbitals, right? It's a system in which you can think about particles that are sitting in quantum mechanical energy states. So how these quantum mechanical energy states come about, it would typically be dependent upon the kinetic energy and the potential energy of the system. And the potential energy is implicit if the particles are sitting in certain orbitals, isn't it? So
Yeah.
So it's implicit there. It's not explicitly there. We are not really taking into account the velocity aspect. You see, velocity is a very tricky thing, because when you talk about velocity, the concept of velocity, the concept of force, these velocity is still there, but the concept of force, for example, is not really there in quantum mechanics. Quantum mechanics is a very, very weird subject. There is no real force operator that we routinely use in quantum mechanics. So you have to be very careful. Our understanding of the subject is not super complete and comparable to classical mechanics. So when you talk about velocity, I don't know. I mean, in quantum mechanical systems, the velocity has a problem, right? Because velocity means that it comes under the Heisenberg uncertainty principle.
Yeah, so then we have the position momentum relation, right?
Yeah, so in other words, when people talk about specifying a system state, it is customary to avoid getting into issues like velocity and so on. Because when you say velocity, you get into a measurement problem. I mean, quantum mechanics has a lot of baggages that it brings in terms of what can be said and visualized and what cannot be said and visualized. So what I'm trying to say is that velocity is not a good word in quantum mechanics. You can talk about the momentum operator or the average momentum and stuff like that. But many of the common, so in other words, the Maxwell-Boltzmann distribution concept in a system of classical particles and a system of quantum particles can't exactly be interchanged. In quantum particles, you have to be more careful about what you can say and what you can measure, because ultimately it is pointless to talk about physics of something if you can't measure it. At least that is something that we assume, right? That's something that we go by. So I don't know how to best answer your question. All I can say is that there are quantities that we are very comfortable with in classical mechanics that we don't want to touch in quantum mechanics. And the concept of velocity is one of them. Velocity, force, these are among them. You can talk about random force, but you can't talk about force. Random force can be thought of as an observable in quantum systems. And I hope to touch upon that in 520. I know I'll touch upon that in 520. And it's a very complicated mess. But here, you can't really go there. Sorry, I can't give you a better answer because it is, I'm not a quantum mechanical entity.
Not a problem.
I'm
Thank you. Such is the problem of studying this field, right?
Exactly. I'm a very classical thinker in my own way, as we all are. So now let's get into fully quantum particles in the grand ensemble. So fully quantum particles mean that we have the structure that we have just set up, but now we can impose the properties of fermions and bosons. Here we go there. So Z of TV mu, the grand partition function, same as before, excepting now what we do is that we impose the conditions on occupancy in a given state. Because you see in the past, in the previous case when we were, oops, I'm going the wrong direction. You see here, or rather, here, we didn't really impose any conditions on the occupancy. It was just like this, and we converted it to a product, and then we talked about an occupancy like this. This is no conditions imposed. We didn't say what S can be and so on and so forth. But now we will. And that is the reason why the sum over all possible NS's now becomes a special sum. And because it is a special sum, there is a prime to mark that. And there is an X here, but the X means for fermions, this can be 0 and 1. Basically, you can have a state which is either occupied or unoccupied. And the occupied state can only have one fermionic particle. And that's because of Pauli exclusion principle. So this X equal to 1 for fermions, meaning 0 and 1 are allowed, NS equal to 0 and 1 are allowed. That's what this means. That is only going to be true because of Pauli exclusion principle, right? Which is a consequence of the spin statistics theorem. But for bosons, this X can go to infinity, right? So therefore, these are two separate kinds of sums. So we do these sums, and so the ZTV mu and goes from 0 to infinity. You write it out just like before, and then you have this product term, like you had earlier. So everything is the same, just written a little bit differently by dragging this e to the beta mu n inside. And then you combine the e to the beta mu n with that term. So you kick that out, which is what you do here. And now you have something that you kind of saw before, excepting this sum is very different. So now from here, you go to the first case, which is there's the fermionic case, but n sub s can be 0 or 1. So n sub s can be 0 or 1 in this case here. You have pi of s, just like you had pi of s before, you had pi of s. And this becomes one term where n sub s is 0. That means this whole term becomes 1. And the other term where this n sub s is 1, which means you have e to the beta mu minus es. And that's what we have here. So the grand partition function for a system of fermions can be thought of as the product over all the states. And each state can be either unoccupied or occupied. That's what you have. For bosons, on the other hand, there is no such restriction. So ns can go from 0 to x, and x can go to infinity. So now you have ns going from 0 to infinity. So that means you have ns equal to 0, which is 1, ns equal to 1, which is just 1 here, ns equal to 2, which will be 2 here, and so on. And because of the way this is, this becomes a series like 1 plus x squared plus x cubed, and so on. And that series, you know, is 1 over 1 minus x, if you sum it up. So therefore, this summation here lends itself to becoming 1 over 1 minus e to the beta mu minus epsilon s. So the partition function for the grand partition function for a system of bosons will be the product over all possible states of factors like these for each s. So now if you look at this guy, and if you look at that guy, you can actually capture them in one generalized formula. So this is the grand partition function for fermions and bosons. So product over all possible states, 1 plus e to the beta mu minus epsilon s to the power plus 1, which gives you this one. So that's for fermions. So the plus sign and the plus sign is for fermions. And 1 minus e to the beta mu minus epsilon s raised to the power minus 1 is for bosons. So fermions and bosons therefore have similarities and differences, and the differences are big enough, broad enough, such that you can have characteristically different behaviors. Again, to remind you that all this is only in 3D. This is not in 2D. 2D is different. And we won't get into 2D, okay, because 2D is very, very interesting and properties are different. In fact, in 2D, differentiating between fermions and bosons becomes a very different kind of process. So
Wait, why? Sorry, that's like a mic drop.
yeah, it is a mic drop. That's why you have the concept of anyons. So
yes, the Majorana fermions and so on. Yes, I'm aware of them. But like, I was wondering about where that fits in, because I know that now your spin statistic's not half or integer. You can have anything. You can have 0.333. You can have 0.17825, whatever.
yes.
So like, what's going on?
Yeah, I must beg my ignorance. I'm not a real expert in it. But so you can actually formulate the statistics of integer spin and half integer spin systems in 2D. And the geometry of the 2D is such that the differences that arise in 3D don't arise in 2D. 2D is a very restricted dimension. 2D severely limits the pathways that you have available for the particles to move around and so on. And as a result, the many particle system in 2D given the influence of the spin, has to be intuitively very different than 3D. I mean, imagine you are restricted to a plane in flat land, so to speak, as cosmologists like to say, and going from one point to another is infinitely restricted compared to 3D, isn't it? Because
Yes, in 3 dimensions, you can go into the 3rd dimension and take arbitrarily long path to get there.
yeah.
Yes.
So what happens is that there are phase relationships that come in 2D that don't have to come in 3D. And so the natural algebra of 2D systems, 2D quantum systems with spin are best described with polylogarithms. That's a natural mathematical tool for describing them. And when you adopt the description of polylogs, it naturally lends itself to the concept of anyons. I know I'm giving a horrible explanation because there is absolutely nothing intuitive about it. But it is tied to the fact that the pathways are very special in 2D. And therefore, how particles move, how particles, what kind of positions the particles can take. Again, position is not a legal word. But what kind of states the particles can realize are fundamentally different in 2D. My personal, you see, we all have our own ways of understanding quantum mechanics. I understand quantum mechanics through operators. And I think of operators intuitively as classical variables. And of course, there are allowed variables and unallowed variables. So I think of quantum mechanics primarily in the Heisenberg picture, which is the operator picture. I think of these operators as vectors in a Hilbert space. I think of the projections of these operators as measurable scalar products. That's how I think. So I try to relate with that picture. This polylog argument, I've seen it done, but I don't remember the details. And we can have a special discussion on that later if you're interested, but I have to do some reading, going back and picking up some of the things that I have.
So just making sure, you said poly exclusion principle, and then logarithms.
No, poly as in P-O-L-Y, poly.
P-O-L-Y.
Yeah.
Oh, poly logarithms. Yes. Okay.
Yeah.
I see.
So the natural formulation of the algebra in 2D is in polylogs. It's not in terms of, it's sort of like when you restrict physics to to specific dimensions, specific mathematical structures come with it.
Yes, I see this now. Okay. Yeah. Beautiful.
And those mathematical structures actually fix, if you will, the proper description. So for the longest time, people didn't talk about anyons as the fundamental entities in 2D. The concept of bringing in anyons as the fundamental entities in 2D actually took shape mostly in the 70s and 80s, as far as I know. Meaning in condensed matter and statistical physics. It took shape at that time. So you don't see it in the books as a consequence of that. Most textbooks don't have it. They would have a cursory mention of that. So when I went to school, this was not part of the diet, so to speak. So I didn't pick up on it. I picked up on it much later in life, basically through talks and discussions with people who were working on that and so on. So my understanding is through that. But unfortunately, to be very honest, I don't have a mental movie of it in my head. Whatever I have, I share. It's pretty elementary. So, okay, so where was I? So one can now look into the equations of state and so on. And so it's a non-interacting system. So again, you expect a non-interacting equation of state. But if you go through the same process that we went through for the statistics-free version, you can calculate the beta PV, which is KT log of Z. So now, of course, when you want to take a log, you remember there's a plus minus 1 here. So if you take a log, this plus minus 1 would come out, which is exactly what happens with the plus minus 1 here. And then KT, this is the KT. And then the log of this gives you the sum over log of 1 plus minus this whole thing here. And similarly, if you want to consider the average number of particles, you can do a del del mu. And once you do a del del mu, then you get the following result. You have to differentiate this term, which is here, and then you can simplify, and you end up with this form. So you can see here that e to the 1 plus minus e to the beta mu minus epsilon s has now become 1 over 1 e to the beta epsilon s minus mu. So this is now flipped. It has come to the left, and that has gone to the other side. And again, plus is for fermions and minus is for bosons. And so the occupation number problem, the NS, is 1 over e to the beta epsilon s minus mu plus 1 for fermions and minus 1 for bosons. Now, if you, coming back to much simpler physical problems, when you have a minus 1, then you have a potential for a problem, isn't it? So just looking at it from elementary algebra point of view, suppose epsilon s is equal to mu, whatever they are. And if epsilon s is equal to mu, suppose you could realize that for a system of bosons, then what happens? Then this e to the beta epsilon s minus mu becomes 1. And then, then you have 1 divided by 1 minus 1. Now, assuming that beta is not perfectly 0, but beta is some finite number, it won't be 1 divided by 0, but it would be 1 divided by some small number, which would make n sub s a very large number, isn't it? So, do you realize what that indicates?
Essentially,
We have a
infinite
giant
population.
Yes. And when does that happen?
When you have an infinite population of things in one state. So
yeah.
bosons.
So it's a Bose condensation problem. So, right?
Yeah.
So Bose condensation, when Bose condensation happens, at that magical sort of condition, the bosons, wherever they were, right, they were hanging out in their own states and so on. And of course, whatever temperature they are under and whatever interactions they have, that would put specific conditions on them such that they would be under some pressure to kind of be in so-and-so energy states. But if the energy states are such that epsilon s and mu, this magical number mu, are more or less equal, then all these bosonic particles are suddenly incentivized to hang out in basically one state. So that is your Bose condensate, right? So the prediction of Bose back in the 1920s was exactly of the existence of this state. And that was a paper he had sent to Zeitschrift when Einstein was the editor of that. And Einstein had noted a little algebra error. So Einstein had fixed that. And this is the reason why it's called Bose-Einstein condensate. Okay. But it was Bose, who was an Indian physicist from Calcutta, my hometown, who originally identified this in the 1920s, I think 1925 or 28, around that time. So that is what later on became this extremely important thing called a Bose condensate. Now, why is it important? Okay, it's a natural question to ask. So as you know, the Bose condensate was experimentally very hard to realize for the obvious reason that putting the bosons in that state was not easy. So Wolfgang Ketterle, who was a postdoc at the time at MIT, under this guy, Kleppner, I think. Kleppner was the advisor. And then two other Kleppner group members, Carl Wieman and Eric Cornell. I think Wieman and Cornell by the time had just become faculty members. Wieman was a little bit older than Eric. And Wolfgang Ketterle had just transitioned from a postdoc to like an assistant professor at MIT, because his experiment at the time that he had done at Kleppner's lab of trying to make a condensate was turning out to be quite successful. So MIT was very interested in holding on to him. They are the ones who got the Nobel Prize in 2001 for those experiments. Interestingly, Kleppner did not get the prize, although it was done in his lab. He was the advisor, but it was the students who did the work, the postdocs who did the work. So, of course, it took a long time, right? It took of the order of 70 some years, because these experiments are very difficult to do. You have to hit the magic conditions such that you actually get to see this condensate. Now, the interesting thing about this condensate is it's a truly many-body Bose particle state, but the particles are hanging out in real space and time as a dense plasma of sorts. They're kind of all clustered in together, and they have a structure. So they don't really have a lattice-like structure, but they have a good enough structure that when you try to visualize them in real space, the system is amenable to giving you some kind of a real picture of what this Bose condensate state looks like. Now, from an application point of view, which to me is always more important than the fundamental physics somehow, because if there is no interesting application, at least I personally find that it's not a complete thing in terms of understanding. So from an application point of view, this is a truly quantum mechanical many-body state that one can see and one can control, and it's not that difficult to visualize. Of course, the state is difficult to make. So anyway, I just wanted to point out that the Bose condensate phase shows up. The other thing that shows up also is that if you look at the Fermi-Dirac aspect of the distribution, you find that if epsilon s is more than mu, then very quickly the number of particles in state S goes to 0. So if epsilon s is more than mu, meaning to the right of it, and if epsilon s is less than mu, then for low enough temperature, which is high enough beta, this number very quickly goes to 0. This part here. So that means ns very quickly goes to 1. So therefore, this has this step-like feature as you go to the low temperature end of things. So this is the story of how fermions are. So at low enough temperature, fermions tend to be in occupied states below what we call the Fermi level. So mu then plays the role of the Fermi level, which is what you see in systems where fermionic particles describe their many particle features. Basically, you're talking metals, for example. Metals you have a whole bunch of free electrons. These are the guys who dictate the properties of the metals. And the metals are fermionic entities. So essentially, then you have this feature of the occupied state at low temperature below the Fermi level, and then unoccupied state at low temperature above the Fermi level. And as the temperature goes up, so as beta goes up, what you find is that, so beta much less than infinity is at finite temperature, and then you begin to see this kind of behavior, much more mellow behavior, much more gradual behavior, where from being more or less all states occupied at low enough, at epsilon s less than mu, you go to the most states not occupied as epsilon s exceeds mu. By the way, it is important to note that beta equal to 0 is pretty much meaningless in our studies, in everything we have worked out so far, because beta equal to 0, the fact that beta equal to 0 is not realizable shows up in a big way by giving nonsensical results. Because here, for example, you see, if beta were 0, then the occupancy would be half all the way through. But this is actually never realized. You don't have half occupancy all the way through, whether you're below or above the Fermi level. Okay, so the other thing is that if you let beta be small, but you don't allow beta to be 0, what you do actually see is that the Fermi distribution now becomes more or less the same as a Maxwell-Boltzmann distribution, which is something that we have seen before. Not a surprise. So in the higher temperature end, the fermions behave very much like their statistics don't play much of a role. That's what it's trying to tell you. Okay, I'm past time, so I should probably stop. But just one more point. This is just the bit of the analysis that I wanted to put on the record to show that a Bose condensate state would be possible if epsilon s and mu become comparable for this Bose particle system. I don't write Bose-Einstein condensate here, by the way. I was going to get into it a little bit more detail later, but maybe I should have written this is the part about the Bose-Einstein condensate. Now it's important because people have seen it, but for the longest time, this was just a little page in a StatMech textbook. Any questions? I think I'm going to finish now.
I do, but I think I'll wait to ask it later since it's so late for you. It has to do with the beta going to 0. But
yeah, I just have to be careful. Beta going to 0 is okay, but beta equal to 0 is not okay. Sorry, no. You mean beta going to infinity? That's t equal to 0, you mean?
No, I meant beta going to 0.
Oh, beta going to 0 is infinite temperature.
Yes, I'm aware of that. And so I guess it's just weird to me that at infinite temperature, assuming that it is truly infinite, meaning that beta is 0, we now get like it gives us a very weird result. It essentially, it's beta going to 0 is essentially the same as you know, being perfectly in one state or each. Yeah, I don't know how to describe this.
I think that is exactly the reason why when you have beta going to 0, I wanted to bring up the issue that this form should be viewed in the right way, and when you view it the right way, then you actually see all you have is the Maxwell-Boltzmann distribution, rather than weird result like that funny result that I drew there. Right, because it's easy to see, right? If you put beta precisely equal to 0, which means t exactly equal to infinity, then you basically get half.
Yeah, and it's constant no matter what. It's like it's just an odd thing to think about.
Yeah. So it tells you that many of these forms in physics, they have to be treated with some degree of care and some degree of trying to understand intuitively what it means. Here, it gives you an intuitively nonsensical result. And then you see that that's not the way to think about it. The way to think about it is as follows. Now, this brings in a point that I wasn't planning on mentioning. But the Fermi function, this particular function that Fermi had, that goes by Fermi's name, this nearly step function like feature. The Fermi function does show up in physics from time to time. And it shows up also in atomic physics from time to time. And there is this particular form of the Fermi function is not a form that should be taken without due care. Because whenever you have functions with this kind of a step-like form, there are not too many good ways of describing them. All the descriptions are pretty limiting. I think Gregor Wenzel came up with a form as well, which is not very different from this. But the forms are very delicate. So when you see a form like this, which lends itself to a step function type behavior, which also means that if you take a derivative which lends itself to a delta function behavior, you have to be careful. Just like when you deal with the Dirac delta function, you have to be careful. Same thing with this function as well. So the fact that it gives you such a gibberish of a result at beta going to 0 is, knowing that is not so much of a surprise. But yes, it is annoying. Not something that I like to see. All right, so we'll have a class on Tuesday, and hopefully I'll be back on Thursday. Hopefully. So
Thank you very much.
Yeah, thank you.
Sleep well.
Good night.
Thank you.
Thank you, Professor.
you.
Take care.
You too. Good night, guys.
I have a question.
Yes, Haidar, tell me.
So, did you get my email about the homework?
I think I got an email. Let's see. Yeah. That's not a problem.
Yeah, I mean, I can screen share right now and show you the timestamp and everything.
No, it's all right. I believe you. There's nothing to. Obviously,
All right.
I mean, normally you're always on time, so obviously there is some problem. I don't have a worry about it.
Okay. Thank you.
All right. Good night.
Yeah. Also, I think it was a kind of a sad day in India today,
Why?
because of the World Cup final.
Yeah, right. Yeah. Well, Australia played very well. So what to do?
Yeah.
Australia played very well. Okay. Good night.
Good night.